Roger, and then he'll hand it to Ulysses and us, along with our other engineering team, put together the slide deck for you to help inform and learn from some of the painful mistakes and learnings of past adventures. So I'm here to educate. Thank you so much for joining and your time. And this is all about how to make a transient load test adapter for ASICs, adapter design steps. My name is Greg Whalen in business development, and you see Roger and Ulysses here as well. And then we have an engineering team in the Portland area. And then Roger, I'll let you take over the intro at this point. Share a bit about LoadSlammer, the company you founded, and the rest of the agenda for the slides.
Thanks, Greg. Thanks everybody for joining. Excellent. We started making these transient load testers a while ago in the quest of finding a way to accelerate time to market and kind of create a common denominator for people to test solutions and come up with the same, using the same methodology, so that we'd spend a lot less time asking how we measured something and how we tested something, and comparing different techniques, and actually trying to have a common platform. And it sort of spiraled into LoadSlammer about 2.5 years ago. Now we're sort of busy cranking away for quite a lot of the tier 1 CPU, GPU, FPGA customers. And the idea is we're just, doing large signal analysis, right? And the idea is that you get good large signal analysis, and you can create a lower, a more efficient system solution in a faster time, and that's what it's all about. So, as Greg alluded to, please chime in at any moment, or just, I think there's a text. You can just text questions in as well if you prefer to do that on the chat window. I think that's a function. So,
yes, absolutely.
Cool.
For any questions, as Roger speaks, if you don't want to like interrupt the flow, you can put the text in there. I'll ping Roger so he can get to it. I forgot to mention too, full disclosure, I do want to record this and send it out. So if that's not okay in the audience, let me know. Or if you ask a very specific question, it might get out there. Yeah, just putting it out there.
Okay, thank you. So I'm going to go through basically half of it, and then I don't know what, from a time perspective, how much it's going to be, but then Ulysses is going to show some. He's just done an adapter design, and it's pretty packed and intense in terms of the connectivity. So we're going to talk a little bit about the actual practical implementation. I'm going to talk a little bit about how to do the selection and some of the pitfalls. There we go. So just a reset on this, our transient load testers can test all sorts of different applications and voltages and powers, but it gets harder as you go down in voltage and the DIDTs get up. It gets harder and harder. So we're focusing on some of the harder aspects of designing an adapter, and that's for an ASIC that's going to go down on a system, typical like a data center type application, so that's just to sort of focus on that element of the design. That's the difficult stuff. So here's the flow we're talking about. We talk about evaluation, characterization, validation. Evaluation is really kind of this is from left to right terms of time, and the evaluation is as you go through time, obviously the cost of getting closer to production goes up. So the point here is that the time in characterization is less than in validation. If you're characterizing ASICs on a pre-printed circuit board, there's less time there, but you do need more in the validation area. You need to do more devices, you need to do more lots, etc., etc. And kind of why I'm highlighting this is because it dictates what kind of type of adapter you're going to make. So you've got to be thinking about, why are we doing this? If we're just evaluating a DC to DC regulator, you could probably just put a connector on and attach a LoadSlammer to do a fairly fast evaluation of the key parameters. But as you go down to the right, certainly in the more sophisticated devices, the choice gets a little narrow, and you have to be a little bit more specific about what you're actually trying to test. So why are we testing it? Is, you know, it's critical. Like, what are we trying to figure out here? And then obvious stuff that needs to be mapped out is like you're basically going to generate a spec sheet for yourself. What rails do I care about? If it's a Xilinx FPGA, like the one that Ulysses will be talking later about, I think it has 15 different rails, 4 that we're performing transient tests on, and then a series that we're sensing on as well. So are you testing? Are you measuring and are you stimulating? Which rails are you? You've got to map that out. And then obviously you've got to figure out what these specs are that you're mapping out, the DIDTs, you know, how many millivolts of noise you can withstand on each rail, and all that good stuff. But before you identify that, or along with that, you need to figure out what kind of testing you're going to do. So we just highlighted some of the tests that typically would be done on an adapter, transient, impedance, etc., etc. And so we're just going to dive into a few of those first. And why we're going to dive into those is because these are where the sort of classic pitfalls can occur. And really, the purpose of this is we get a lot of guys asking us. So you know, we design adapters for customers all day long, right? But sometimes the customer wants to do it themselves, and what we don't want to do is have an unsuccessful customer experience. So the idea is to like point you in the direction of what not to do if you want to take this on yourself, and maybe after seeing this presentation, you consider it more of an endeavor than you'd first expected, and so you give it back to us or somebody else to develop.
Mm-hmm.
So we're going to go through some of the tests, and then the connector. You know, do we use a connector? Do we not? Etc. Etc. Okay. So first things here. This is like this is just to make sure everybody. Yes.
Sorry to jump in. I wanted to ask: did anyone have questions from the last slide? That's sort of the agenda and the why with the flow. Good. And then I did have a question, Roger. You were mentioning, are we testing and measuring? And then I also liked what you talked about in characterization and validation. Would you mind delineating that again? I think last time we spoke about this, one was more of a sampling methodology and the other one was higher volume, and those two present different challenges.
Yeah, so thank you. So the validation, right? If you're this is where I see that the manufacturer of the high volume solution needs to validate a number of systems. So it's about test time and volume. So you may be wanting to go with some kind of solution that can be swapped in and out quickly. So like some kind of socket technique versus characterization, where you may only be doing 10 boards or something like that, right? And you can solder something down, and there's lots of boards that you basically can just use for characterization, and then they just get thrown away eventually. But for validation, you're doing a lot more tests on a lot more boards, and you might want to be able to use some kind of reusable connection for the validation, because there's a lot more going on. Also, with the validation and characterization, you've got to think about the test time, and that's really, test time is going to be governed by the pulse train, or what we call frequency sweep, the classic 3D sweep stuff. And that is going to be very time dependent. And if you have a continuous power, if for example, you're using one of our LoadSlammers that's can only have a continuous output power of 25 watts, but your solution is a 250 watt solution, you're going to be 90% of your test time is going to be in dwell whilst you're waiting for the safe operating area of the power consumption to stay within the bounded conditions. So thank you for highlighting that. I forgot to mention that. Yeah.
Thank you. Yeah, that's great.
Okay, so here's what we got here. This is just to keep everybody on their toes, and we call this fake slews because yes. Hello.
Still here. Yeah. No, I like it.
Okay. So here we go. This is recent scope shot data we took, and what's going on here is this is from a third-party evaluation board, and what you can see here is actually they're claiming this yellow line is the slew rate, but actually it's the red line here, and we can tell this for a number of reasons, but the key point is that don't believe what you see. And we can go into greater detail about what the classic pitfall here is, but basically if you measuring current is really tricky, and Steve Sandler on the call can attest to that. So you really got to know what you're doing to measure the current accurately. And you've got to take that into account when you're designing the adapter. Okay, whether you use, even if you're using a homegrown solution, measuring that current is really difficult. Because of course, if you insert anything into the loop to measure it, you're adding inductance, and the whole thing here is to keep the inductance to a minimum to increase the slew time if you need really fast slew rate. So here we go, fake slews. You saw it here first. Okay, so what the actual slew rate here is it's like 1.5 microseconds versus I guess it's like it's like 40% of 400 nanoseconds. That's what they're claiming. Okay, so let's just look at here. We've got I just pulled this out from a bunch of sweeps we did on a board in the lab, took some snapshots. And basically what we're saying here is, per the previous slide, it's difficult to measure current. So you need to measure current, and then also you need to be able to reference again. So you can see here that in our GUI, we call out what there's always a deliberate gap between the blue line, which is the intended slew rate, and what you're actually getting. So top left-hand corner, everything on the top row here is the duct is at 1.4 volts, and at the bottom is at 0.6 volts, okay? And what we've done, and then from left to right, we're going from 100 amps to 300 amps. So 100, 200, 300 amps. And you can see that the most beautiful edge is 100 amps at 1.4 volts. And then you can see it starts to do some bizarre things and really starts to roll off here. And that is because the overall aggregate ESR and inductance of the system, including the adapter, is not sufficient to do. So what the key point is, if we're testing at 1.4 volts, 100 amps slew rate, then we're golden with this. This is good. But if we wanted to do more, then we need to address what's going on with the design. Okay, so critical to getting the specs is identifying what your target DIDT and your ceiling current as well. Okay, so that's a salient observation from this test, from this slide. Any questions? Good. Okay. Okay, so here's like a good example of what's going on. We're busy slewing at 3,800 amps per microsecond, and then suddenly it starts to pinch off halfway up, and we're trying to get to, I think in this example, it's trying to get to 600 amps. And it gets to about 300, and then basically somebody puts the brakes on, and it goes down like an order of magnitude in terms of slew rate, right? And so this is just reaffirms, like if you're going to 300 amps, this solution is golden. But if you're going to 600 amps, you're not going to make it because the slew rate's not going to give it to you. Okay. This is some data we took really recently, and it's kind of cool. And some points to why we do large signal impedance and why you do that, how to design an adapter for that, is that multi-phase regulators, digital ones, are not linear. They have a non-linear impedance. You look at the analog solution, it's beautiful. It's like the classic Brontosaurus shape on the right-hand side. And then I don't know how to describe the one on the left, but this one on the left is, you can see that there's obviously some non-linearities, and if you're designing a PDN curve to fit on top of this, you've got to account for this, I don't know how to describe it, but this infraction, maybe, on the left-hand side. So the point is, analog control loops of yesteryear, yeah, they're terrific. They offer some great smooth linear responses with respect to impedance. And digital do not, because they have all these like non-linear, constant on-time type functions inside the control loops. I mean, you've got to think any kind of control loop is non-linear, right? Because amplifiers will get saturated, and the discrete components have non-linear characteristics as well on the board. This is why you have to do a LoadSlammer, You have to have an adapter to measure where it matters, and you need to measure the actual, the large signals that you're anticipating in the load. So clearly, digital multi-phase regulators are nonlinear, and that's done deliberately because it helps accelerate some of their transient performance. But the question is, what would happen? This points to the board that we developed, just got built up yesterday, and this is offering the beautiful smooth performance. But there's two Vicor modules that we're using in there, textbooks or analog controllers there. So the point is, we did a large signal analysis back here. This is 100 amps offset, 100 amps sine wave. Where's my cursor? There it is. Bottom left, you probably can't see it, but it's 100 and 100 down here, and it's 100 and 100 here. So it's 100 amps offset, and we're stimulating the PDN with a 100 amp peak-to-peak sine wave from 1 kilohertz out to around a megahertz. And you can really see it starts to sing here on the left-hand side. Now look, what happens if we do it with 5 amps? Suddenly, that nasty hump has disappeared. So on the right-hand side, it's 100 amps sine wave, 100 amps offset. On the left-hand side, it's 5 amps sine wave, 100 amps offset. What does that tell us? It tells us that the measurement has to be, the measurement we take has to be relevant to the anticipated slew rates we're going to subject the final system to, right? Otherwise, all the material is, the testing is irrelevant. So this points to what would be, this is our smallest sine wave we can stimulate the system with. But, so we would classify that, and for the sake of argument, a small signal versus a large signal event. And you can see the results are very different. So that is something to be aware of when this is a really good test, very, very important, and definitely the adapter needs to be able to handle this kind of testing.
Roger, a quick comment. There's another thing that emerges when you look at these two with the much smaller current swings. What you're exposing there is like a signal and noise ratio in your digitizer for your voltage. It's much easier to measure larger voltages than smaller voltages. And so I believe what you can see here is with the large currents, because of the low impedances, you're talking about very low voltages generated across those impedances, right? So it sort of helps. It helps that the FPGA loads themselves, let's say it's FPGA, are going to probably have some dramatically large currents to begin with, but that helps in your measurements because your voltages you're measuring are larger across these small impedances.
So what we need to do is actually, we're going to change the way we're sampling is that you can see that it gets noisier at the start of every decade. So we're going to change the way we're sampling. So we're going to adjust the amount of samples as a function of the frequency we're sampling to get that noise down. But you're right, the signal to noise ratio gets a little gnarly down when you're only slewing 5 amps, right? And there's a lot of range that you can measure. So yeah, you're absolutely right, John. Yeah. So, but yes, so there is definitely, we're going to basically change the sampling rate down here to capture more relative to the frequency that we're measuring at that time. And in fact, you can see it here. It's like just a little bit noisier than here, right? So look, key observations from this. You need to be able to measure the current accurately. Don't believe in fake slews. There's a lot of that out there these days, especially on customer evaluation boards. So watch out on vendor boards. So just watch out for that. Make sure the time constants and what you're measuring is it's accurate. And Steve, I believe, has a course coming up and is able to talk about that in a lot more detail. Steve, a bit of shameless promotion for you.
Thanks, Roger.
You're welcome. The slew rate is a function of the peak current, the destination current, and the voltage of the device under test. I showed you in those 6 snapshots earlier. And that digital multi-phase regulators are nonlinear, so you really need to get a handle on the time domain and the frequency domain response of these guys. and you have to measure them with the appropriate stimuli that you're anticipating on the load, right? So if you've got an FPGA and it's going to be stepping from 100 to 200 amps, you really kind of want to sweep it like we did with 100 and or maybe even a greater sine wave stimulus than we would 100 amps peak to peak, so it's 50 plus 50 minus, but maybe you need to set it for more. Just depends on what the what your test conditions are. And this really is something that Steve drove with us recently, is to make sure that we can validate what we're measuring, and everything we've got in this data is all being examined 2 or 3-fold now in terms of and we end up building all our own boards to test this product, because if you don't, then you end up with some crappy PDNs actually from our friends. The evaluation boards are designed for certain reasons, and they don't offer the best PDN per se necessarily. So we basically have to create our own reference boards so that we can get a baseline on the data we're capturing. So there's 3 ways to build an adapter, right? You can use a connector, and this is the LSP 1000 that we showed a couple of snapshots of earlier. And rule of thumb, 1600 amps per microsecond. Just all these numbers in the yellow are based on a 60 millimeter by 60 millimeter footprint so like in the middle picture, you see this guy. I think that's a 60 by 60 type footprint, 60 millimeter by 60 millimeter. So what we're saying here is that you go up in edge rate from left to right. Okay. Now look, on the right hand side, we have what we refer to as the fringe lunatics. Okay. And these guys are soon going to be the norm. So, and this is going to be, one that will soon become a point of load experience. So what we have is different solutions for different slew rates and different applications, whether your characterization. This is a great opportunity. If you want to just do a hot swap on an ASIC, you've got to just do some, your DIDT is not super fast, and you want to check a variety of different boards. You can put down a connector, get the information off the website, put down a connector, and you're off to the races. It's golden. But if you need higher DIDTs, then you need to go with what I refer to as a down solution or an active adapter, and that would basically be an active adapter. You guys want, you design it yourselves, and then you can plug the brain into it, and that gets you a lot higher DIDT. But it's also, as we've talked about before, it's a function of the DUT voltage as well. And we're going to talk about a little bit about how to calculate where to position which solution you're going to work with. And then of course we have the high-end solution on the right-hand side, which is as I refer to as the fringe lunatics. But they're getting, this is going to become the norm in the next 2 years. This will be the standard operating procedure for a lot of these bigger ASICs out there. Now with all of these, you can see that we did that impedance analysis. So the cool thing about with an adapter is that we can get an S parameter extraction from that large signal impedance. So you turn the large signal impedance into an S parameter file, and that can then also help you with your design constraints. You can actually put that into your CAD system and use that as part of your design rules. But it just depends on what the target devices you have, and how tough the problem is, and that will dictate the level of complexity of your adapter. So this is kind of like a Mickey Mouse graph I put together, and I kind of just put it like active versus passive. Passive being this guy on the left with the you just put him in a connector. It's a connector. It could be called a passive or connector solution. And I just put it into these 2 buckets, and really, we're just going to go into a little bit of theory of what's going on here. Okay, so here's the, I pinched this from Dwight Larson, did a few articles on transient load testers. And I think somebody from Maxim's on the call, so say hi to Dwight when you're back at the factory. This is like a classic constant current load slamming circuit. And, you know, it's a nice sort of representation of what's going on. Of course, what we're missing here is our friends, the impedance, you know, the inductance and the series resistance. And what you've got to really do is figure out what your budget is. All of this theory comes down to what's your DIDT, what's your ceiling current, because it's going to be gated. Those are the gating items on how you're going to design your adapter. And you need to create a budget, an impedance budget, and figure out if you're in budget, you've got to stay under budget to hit your requirements. And you can see that there's three key elements. You've got the resistance, the inductance, and then you've also got to think you've got some switching element here. If I go back here, it's a little clearer to see. You've got this FET. And that guy has to stay on. But for him to stay on, you know, the function, there's an equivalent resistance, which is a function of the drain source voltage, right? So you need to make sure that this doesn't pinch off too much. And what's going on, this right here is where it's pinching off. So you've got to take that into account when you're designing your adapter. And this graph here is, I just took this out of it. This is not the signal path of our device. But you need to add all these impedances together in series, and then take into account you need a minimum headroom to turn that FET on and off with that amount to give you a certain, keep the ESR under a certain threshold for you to be able to hit your maximum current and the slew rate you're intending on hitting. You guys got any questions on this? Exceptional, thank you. Okay, so here we go. This is kind of like another representation of the previous slide. And this is like a classic CPU testing system where you go from the system is the printed circuit, or like the motherboard, right? And then you go through some kind of interface, and then maybe what it may commonly referred to as an interposer. And every time you go through these steps, you're adding inductance, and you've got the slamming agent itself. In this, I put it as 1 nanohenry for the slamming device, because I'm just using the data we use for our LSP 1000, which is very conveniently and unintentionally 1 nanohenry of inductance and about 1 milliohm of resistance. And so it's very convenient, and it certainly wasn't intentionally. We designed it to be as low as possible. So that's just a side note. But you can see the chain. This is part of the budget. That's got to be calculated, and then you've got to back that out to see if that meets your requirements. Otherwise, you've got to go back and rehash it. This is kind of like a reusable solution. We were talking about characterization versus validation. So this is great, you know, for higher volume, multiple platforms or multiple solutions that you've got to have tested. Then you want a reusable solution if at all possible, but you may have to go with a down solution, because this budget really starts to get eaten up quite a lot when you get into the more sophisticated, higher gate count, lower geometry ASICs out there. They're really pushing the elements. And of course, what we've just discussed is the voltage is going down. So that's fighting against you, but the slew rate's going up. So you've got two things you're fighting against. So, you know, be warned. So there we are. There's 3 key calcs to figure out how your adapter is going to fit in. You've got to get your budget. So, and the 3 calcs are, you know, the Imax is basically ohms, or, you know, volts over, it's just the resistance of the solution. And the voltage and the current that you want to get to, and then the DIDT. I think I did that. I did this late last night, so I think this might be wrong. I'm going to scratch this slide. And then the DIDT is obviously critical for the actual edge rate, and then you've got to figure out what the switching elements you're using are, that and where they're going to pitch off when you're doing your when you're switching this element on and off, if you're using like a classic kind of implementation like this. Okay, guys, got any questions? I feel like it should.
I just want to say that that's my fault, Roger. I'm not as smart as you engineers, so I didn't catch that on the equation.
No, thank you, Greg.
I took some courses.
Take the bullet for me, thanks.
Right. That's right. Also, I want to check in on time. We're just past the half hour. So I know Ulysses I don't want to squeeze him too badly, so just a heads up on that. If we want to have time for Q&A and everything.
Yeah. Okay, so I alluded to this previously, but like this is the impedance of our LSP1000, and it's very elegant. It's like, I mean, we did try and design it to be as low as possible. It turned out to be pretty accurate at 1 milliohm and 1 nanohenry. And that's not a rounding error. It just kind of fell out like that. So so if you are designing your adapter and your LSP1000 as a target device, you can put this into the budget for your adapter to design. Okay. Now the thing is also the LSP1000 is parallelable, so you can stick one, two. I think we've had up to 4 in parallel for people that really need to. They want the hot swappable solution, the connector option, but they need faster edge rates, so they need to drive this number down to hit their specific criteria that they were designing an adapter for. Okay, so to summarize, this is kind of wrapping up my portion of the conversation. The design requirements are going to, you'll get forced into, as typical, design happens, you get your specs and it pushes you in a direction that solves your problem. And the sooner you make, there's some critical decisions you need to make, and really I've summarized them in a shrunken version of the slide we showed earlier. Kind of puts you into 3 buckets. Like, what do you want to do? You're going to go with this. This is the sort of the most convenient, but these are like more performance driven. And make an impedance budget, and then figure out, based on your spec, you will drive an impedance budget, and that will dictate your strategy. Okay. So you guys got any questions? We're going to hand it over to Ulysses, and he's going to talk through a recent design he did. But if you've got anything you want to talk about right now, just interject.
All right.
Cool. This guy, I'm just going to, so Ulysses, you about?
Yeah, ready.
Hey, thanks. This first slide is, you can see, is an LSP 1000 dual configuration we did for, I guess it's a VCU 129. That's a picture of the overall board. What we did, and I think this is close to the design specs. I think we may even just put some generic numbers in here for the sake of argument, because it's just, we all know it's the usual sort of type of voltages. But there's a good example of one of the designs that Ulysses did. And then I'm going to just put it onto Ulysses. You want to start talking through, how you go about the various stages, and then I think you're going to show some simulations, because what happens, you got this budget we were talking about previously, right? You got to make the impedance budget, and obviously what you can do is you can extract all your, you can.
Anybody else losing audio on Roger?
Yes.
I'm losing.
Yeah, a little, thank you.
Yes.
The bandwidth, Roger, it's too much for the networks. Too much knowledge.
Yeah.
How about you, Ulysses? Are you still coming through?
Yeah, I think I can go from there. Are you controlling the presentation?
I got it.
You got it? All right, thanks, Roger.
Okay, well, first, apologize if my pronunciation is not correct. So English is not my first language. So as Roger mentioned, this is like an adapter board we did for this silence board. So I think if you go to the next slide, I will show the standard flow we follow to create those adapters. Can you go to the next one, please?
Are you, oh, let's see. I'll make sure who's host here.
I'll stop sharing. There you go. And you can, Ulysses, you can share.
Well, I think, I will show the real boards, and then we need to go back to the slide. So let me just share my screen. Yeah, you need to allow me as a host.
Oh yeah, sorry. Roger, I made you the host. You have the power.
Hey, Roger.
Oh, looks like we're losing his audio again.
Yeah.
Apologies, team. Will we get this back up for you? Right. Security.
Well, I think I
Okay.
can continue talking maybe while we resolve the problem.
I'll take this easy. Yeah, I'm gonna loop Roger in via dial-in. So yeah, please go ahead.
Yeah, we basically follow the same standard flow on any PCB design. So we do some design kickoff to capture the requirements. As you know, we need to develop the schematics, symbols, and we also need to get some part numbers. We need to also know what kind of interfaces you want to have, like the connector sizes. And it pretty much will depend on the current testing or the current values you're gonna do. And in order to properly do the board, we need to consider take a few consideration on the stack up and the size. It's critical to also know if we are going to use what kind of device, because pretty much we are doing a VGA type of PCB. So it's critical to know the manufacturing capabilities of your fabricator, because that will also depend of the BS structures you have, and some decision must be taken when you do the LoadSlammer, the adapter. Sometimes you might need to use some HDI technologies. Some component pitch will allow you to use true BS, which it will also save some money. And pretty much what you need to be considering is to do some also simulations on the voltage drop, or what people call IR drops. Let me see if I get now the permissions. Okay, pretty much what is critical on this design is the properly select the stack up and the layers. Also, sometimes when you do simulations, you might end up to be using some high copper weight into the inner planes, just to minimize the voltage drop, and also to reduce the thermal resistance of the board. Because when you connect or solder this board into the other one, there might be some thermal connections between the two boards. So you want to minimize those effects from one board to the other one, and vice versa. And we are able to use a software that allows us to also calculate the mutual inductance of the net, so we can put those values into or calculations into the LoadSlammer. So that's the one that is shown on the screen. It's a test board we did with some basic setup into the software. We have 14 nets. That means it's 14 little small planes, and also 3 of them are with sense lines. So we are able to actually get the voltage drop across the board or the connections. And the board was made of 6 layers, and we were able to use one true via, because the VGA pitch, it was 1 millimeter, so we were allowed to use 1 via. But if it gets smaller, we might end up to be using HDI technology. Can you go to the next one, please? So that's pretty much the one on the table on the bottom is the inductance matrix on nanohenries. So you can take the budget from those values and and you can see the real values on your adapter board. So you can take those values into consideration. So you can see on the middle of the slide, that's the temperature increase into the board. That's shown on the top layer. You can see we have a delta T of 6.2 degrees, and the maximum voltage drop on the net in average, it's 17 millivolts. So the picture on the bottom right is it's a picture similar to those taken from infrared cameras. So you can visualize where are the spotlights. It is important into these boards where you don't have active components where the heat is created. So due to the currents flowing into the inner layers, you might have a higher temperature on the inner layers than on the top. So you will not be able to see those values with a normal camera. So it's important to take those into consideration. You go to the next one. I think that's the last one.
I wanted to mention, make sure that the connector information that we use is here. I'm seeing that my internet connection is unstable. And then there's two other points on this deck. Is this is the connector information that for the Samtec connector, and then the last one is you want to talk about a cope is making sure you can manufacture this thing. It's really hard to, you need to pay a lot of attention to the solder mask and how you're going to add the balls to your adapter and make sure that this thing is flat. So that's really, after you've designed it, of course, you have to manufacture it. It's pretty obvious, but this is not to be overlooked, this manufacturing, right? Especially if you're just doing it in small volume, because you're going to have a tough time getting somebody to pay a lot of attention if you're only building 5 of these. So that's something we wanted to highlight to you guys. And I think that really is the wrap up for the material. I feel like we got through that in a very good clip.
All right.
Questions, guys?
Thank you, Ulysses. Thank you, Roger. So we've got some time left before a hard stop at 1 p.m. Want to open it up to the folks on the call. Any questions, hypotheticals? Feel free to ask and use this as a resource. And hey, it'll help some folks maybe later who watch the recording.
Yeah, so we'll modify the deck and we'll post it on the website.
Yeah, I like it. And then Roger and Ulysses, anything that popped up in your head, like, oh, I should have mentioned that, or anything like that you want to share with the crew, a little last gem for the folks here?
Well, from the PCB design side, it's very important to know your manufacturer, because you can start with your design rules, but at the end, if you go with one fabricator, you might get some surprises. So it's important to know your fabricator, their capabilities, and apply those rules. But also it's very important to do some preliminary simulations, but of course post layout simulations to know what are you gonna get or what do you expect from your board. Because at the end, as any interconnect on a PCB designs or interfaces, the target is to make kind of transparent interconnects. So you want to minimize a few characteristics of the board. So it's good that you are able to use some simulation tools that's similar to the ones we do. And of course, we validate all the products we do. That's pretty much what I wanted to add.
Great. Thank you, Ulysses.
Welcome.
All right. Well, thanks so much for your time, team. I know everything's very busy today with life in and out of work and adjusting. So really appreciate it. Any questions after the call, you can email us, reply to the meeting link, or find us there. Any channel that works best for you, LinkedIn or email. I know we know a lot of you work with you guys also in your companies. But thank you so much. Enjoy the rest of your day, and we'll be sending out the recording for your reference.
Thanks, guys.
Thanks, bye. Yep. Cheers. Bye. Bye.